Hello everyone, so in this video let us talk about the first three problems from the latest Leetcode Biweekly contest 102. So let's start. The first problem is find the width of columns of a grid. Don't worry, the problem statement seems a little bit vague at the very end, but at the very start actually, but it's pretty much simple. The problem statement goes like this, that you are given a zero index m cross n integer matrix that is of the name grid, as you can see in the input like this. Okay, here. Now the width of the column is the maximum length of its integer. Focus on here. The maximum length of the integer. What is the length of an integer? Actually, the length is like this. That it has 3 digits. Okay, so that is the length actually. Don't worry, we'll take some example as well. So moving forward, what it actually states that yeah. So for example, that is given to you the width of only column 3 since minus 10 is of length 3. Okay, so as you can see, this is a column. Okay, so if you draw this complete grid, it will be like this: minus 10, 3, 12, because these are row. Okay, and every row has one element, so it will be like these 3 rows, and this will be a column. Okay, so what is the length of the integer? So length means like what is it is the length. The length means like if you just convert this integer to a string, it will be a string of length 3. Why? Because it has -1, 1 and 0, so 3 characters you can say. Okay, so this is the length of the integer that is actually expected you to find out for every column. So this is often like a matrix of you can say 3 by 1, 3 rows, 1 column. So similarly, you're given a matrix in the input, and you just have to find out for every column what is the maximum width of it. The width is the maximum length of an integer in a particular column. Okay, pretty much simple if you understand the problem statement as of now. So what we'll do is that we will just do a column wise traversal, not a row wise traversal, but a column wise traversal of this complete grid. That is, we will take every column one by one and traverse over all the rows of a particular column, and just find out the length of every, let's say, integer in that particular position, and just find out and maximize it over all the positions in a particular column. Okay, that is the overall idea that we will be using here. Let's move on to the code part now. Nothing much complicated here as well. So that we have taken the inputs of the dimensions of the matrix, and this is the number of columns that we have that is defined here. Then iterate over every column one by one, find out for every column the maximum. So we'll initialize maximum as 0 for every column, and then iterate over every rows for every column, and first convert that particular number that I'm on. That is, as you can see, that this is the column, so that is j. This is column position, that is the row position. That's why this j comma I is the grid value converted to string. So I've converted that particular number or integer, you can say, including the negative, to a string. So now we have the string, so you can directly just easily find out the length of that string. That is the actual you can say width of the particular column, and we'll maximize it over all the numbers. And the end, when we have iterated over all the columns for a particular row, I will actually store that particular width in the answer file for that particular column. I just print out all the widths of all the columns of that particular matrix. Pretty much simple. So that's the whole idea for this particular problem as well. You can pause this video and try to look at the solution of your own as well. No problem. Let's move on to the next problem. The next problem is find the score of all the prefixes of an array. It's pretty much straightforward. You are given that the conversion array convert of an array ARR is as follows. So convert of I is a of I plus the maximum of the array values from 0 till a of I. Okay, so the ith convert value, you can say, or convert value, you can whatever you can say, is the ith value plus the maximum of all the values from 0 till I. Okay, so that is the ith value, and then the score is the sum of all the values. So as you can see, that we also define the score. The score of an array of ARR is the sum of the values of the conversion array of error. Okay, so you just have to find out for the every prefix. If every prefix is an array, find out their score. Okay, so score is actually just the summation of all the values in the convert array, and the convert array ith value is error of I plus the maximum of all the values. So it's pretty much simple if you understand it. Nothing much complicated here as well. So what you can see is that error of I plus the maximum. So maximum till the ith element, and if you have, let's say, any element, if you take the maximum, keep on appending, like what is the maximum for this element, what is the maximum for this and this, maximum for this and this. So it's pretty much simple. Just take the ith element and just add, or not add, like append it in the maximum till now. Okay, so let's say I find out the maximum till now, like this, the maximum of all these elements. If I've taken this element and want to find out the maximum of all these 3 elements, I will take the maximum of all these elements and just maximize it with this element as well, and I will find out the maximum of all these three elements. Pretty much simple. So the ith converter of I value is the ith value plus the maximum of all of the ith values all. So what we'll do is that we will iterate over this nums of I. We'll take the ith value and we'll keep on also maximizing the ith value till the ith point. That will eventually will give us the converter of ith value. Now we will also like keep on adding this converter of ith value, so we will be getting the score till the ith point, and that is the prefix value, and we will just keep on printing and storing that out. Pretty much simple, nothing much complicated here as well. So let's move on to the code part now. It will become more clear to you as we move down to the code part now. So let's see the code part. So what we have done is that this is actually the answer, the score, because we have n scores for all the n prefixes. Let's say array. I will show that in this because it will be long because the constraints are pretty much as you can say large. So this will be the maximum till the ith point, ith number. So the first number is the first number itself. So I will initialize it with nums of 0. Okay, then iterate over all the numbers one by one. First maximize the number till the ith point, because for the converter of I we will require the maximum number till the ith point. So we'll first maximize whatever maximum I have till now with the current number I have, maximize it so that I have the maximum till now. So now the convert of I, that is, this is the answer. This is actually the convert of I value is nums of I, that is the current number I'm on, plus the maximum till now. Now we have convert of I. Now what we'll do is that this is the current score. Okay, because score till I, because this is the score convert of I. So convert of I is score. So actually the score is the score till now plus the current element. So the convert of I. So convert of I will be added here plus the score till now. So score till now will be stored in the score array. So whatever till now score will be, as you can see, score is also adding all the values till now. So the I minus 1 value will be storing the sum of all the scores till now. Okay, because actually if I have the score, what score is? Score is the summation of all the convert values. Okay, so if I have the score addition of all the values till now, and if I've added a new score, I will take the previous score and add it to here. Okay, because score is actually the summation of all these values. So I have the summation of all the convert of I till the I minus 1 point. Now I have added another I, so I will take this score till now, added the score of the ith convert of I and the previous all the scores, and I will get the new ith score. Pretty much simple. You can just take a look at the code as well. This is here because this condition is here because I will not add for the very first element, because for the very first, so I am adding score of I with score of I minus 1. So I will only add score of I minus 1 if I minus 1 exists. I minus 1 exists, let's say for I equal to 1 and moving forward. But if I equal to 0, there is no I minus 1. So I will have to check the condition for it, and that's it. Now you can handle this condition in different ways as well, depending upon your use case and like how can you write the code as well. But yeah, that's the overall idea for this particular problem as well. And if you still have any doubts, you can mention in the comment box. I will be very helpful to give solutions to all of them and take a look at all of your doubts. Okay, let's take a look at the last problem. So I'd already actually also will be posting another video in a while for the cousins of binary tree 1 problem. So stay tuned on my channel as well. But this is the cousins in binary tree second problem, because it is actually in the problem statement of this context. That's why I have been solving it here, or else I will be making a separate video of it as well. But yeah, let's take a look at here. So you are given the root of a binary tree, and you have to replace the value of each of the node in the tree with the sum of all its cousin value. So for every node value, you have to find out the sum of all its cousin value. Okay, and just print out there. So what cousins is? Cousin, if you understand, cousin is that they are at the same level as you are on, or you can say at the same depth. So whatever is your depth, these are the levels, as you can see. Okay, of a binary tree, if these are the levels, so they should be at the same depth or the same level, you can say, but they should not be of the same parent. Okay, so these two are siblings, you can say these two are siblings, but this and this, like these two are cousins. Why? Because they are the same level, or you can say that like a cousin means that they are the same age, so you can say that they are the same depth, so they are the same age, you can say, just as a cousin nodes. So the same let's say depth, but they are not of the same parents. So their parents are different. This node parent is 4 and this node parent is 9. So they are the same level but different parents. That's why they are called cousin nodes. You have to find out for every node what is the sum of all their cousin and replace its value with that. So as you can see, for this there is no cousin, for this there is no cousin, there is no cousin. For this the cousin is 7, for this the cousin is again 7, for this the cousin total sum is this 1 and 10, that is 11. Okay, I hope you understand that's the overall idea for this particular problem, like the overall question statement. Now how can you find out the actual logic for that? uh, if you just visualize the tree a little bit long, then you can try to find out some more observations. Let's try to draw the complete tree thoda little bit more. So let's take an example that I want to find out for this node. So I have to find out the sum for all the nodes that is not from the same parent. So apart from this node, I have to find the sum of all these nodes. I hope you understand. So the overall idea is that, like, instead of finding out again and again, why not I just find out the sum of all the nodes of this particular level? Okay, why not I just do a level-wise traversal and just find out the sum of all the nodes one by one of a particular level? That can be done in O of n, because I will just do an O of n level order traversal over this complete tree and just find out the sum of all the nodes, not thinking what the cousin and all of that is, just finding out the sum of all the nodes in a particular level. Okay, then I can just store it in some array. Okay, the sum of the all, like this node, this two nodes, this four nodes, and so on. Okay, so I have already get a level order traversal and I can just find out all the, let's say, you can say all the total sum of all the nodes. Okay, now after that, for every node, just check I have the sum of all the other nodes. Okay, so what I'll do is that if I want to find out the value of this node, the value of this node will be the sum of all the other nodes except for the value of this and this. Pretty much simple. So I will just find out for every node what is its value, and if there is a sibling of that particular node, what is their value. Okay, so for that also I can just directly just do a DFS over this tree, and whenever I'm on some parent of any node, like let's say if I'm on this node, let's take an example that I'm on this node. If I'm on this node, I will check that whether the left of it exists. If the left of it exists, so I have to first find out the value for that. Okay, for the value for that, I have to check that what is the level of this. The level, I already know the total sum of this. Whether there is a right child also of this. If there is a right child, subtract the value from the total sum, this node value and this node value. Okay, and then whatever value is left will be placed in this node and this node. Okay, and then we'll keep on doing the same thing for other nodes as well. For every node, check there whether the left and right node exist, or like if only left node exists, just subtract from the total sum just the left node, because the right node doesn't exist, it doesn't have any sibling. So from the total sum, because I've already done level order traversal, the total sum will be of only the left node, and the total sum will be subtracted here, and whatever will all are there are the cousins. So we'll get the total sum, subtract this particular node value, I'll get a total sum of all the cousins and just put it here. So I hope you understand the total overall idea what I'm trying to do here, and that's the logic that we can use. So it will be O of n for level order traversal, complete building of this, let's say total sum of all the levels, and then again DFS of O of n for finding out or like modifying this tree according to the complete answer. So it will be done in O of n only. Let's take a look at the solution of it. There are multiple approaches as well, and the code also, you can say that this is not the very like the complete very best code, but yeah, I've tried to write the code very like as clean as possible, and the logic also very simple as possible. So what we have done is that we have to first find out the level sum, the level ordered sum for every level, you can say. So for that we will just do a level order traversal. It's just a BFS over the complete tree. If you haven't seen my different videos on level order traversal, or you can check out on the YouTube and just come to this video again after understanding level order traversal. So level order traversal is just a BFS over the complete tree. So for BFS, we will make a queue, as you can see here. Push the very top node, and just let's say what we'll do is that we will keep on iterating over this node until this queue becomes empty. So whenever I am on the queue, I will again find out the length of what all elements are there in the queue, because that denotes a level. So I will iterate over a complete level. So this while loop is the level, and this while loop is actually doing the traversal over this complete tree, that is the BFS. So this is the BFS, and for every BFS, for every iteration of a BFS, for every level, I'm doing this while loop. Okay, so this while loop is iterating over a complete level. For every level, take out the element and just find out the sum of that particular element, and just push down the left and right node of that particular element in the queue again for doing the same BFS again. And after iterating over a complete level, I will push back the total sum of all the elements in the complete level in the, let's say, in this vector, you can say, of level sum. That is, this level is done, the next level is done, and so on, and keep on iterating over every level and just pushing out all the sum. So now I have all the level sum. Now I have to traverse the, or actually modify the, let's say, tree. So for a tree, the first node is obviously and always 0. Why? Because there is no actual cousin for that. So the answer will always be 0 for the top node. So if the root node doesn't exist, then it will be like just don't do anything. But if it exists, then make the value equal to 0. Now I will call this GFS function on that particular tree, saying handing out the root, the level sum, and the level I am on. Okay, and this is the root. Let's see what I'm trying to do here. So this is the root node. Now what we're trying to do here is that we'll have to first understand that in the DFS, it's actually a recursive function. Recursive function, we have a base condition, then calling the tree node on the left hand side, right hand side, that is the recursion again, and then the base condition, or actually like return thing. So this is the base condition. The base condition is here. This actually this here actually as well, and this is the actual, you can say again, recursion, and then we just return on this particular program. So what is the base condition? The base condition is that if we go out of bound of this completely return, okay, then if you're not out of bound of the tree, then what we're trying to do here is that in the DFS, if the left node doesn't exist, okay, then we have checked it. But if it exists, then what we'll do is that I will append the value. So what we are trying to do here, if we just go above, what we are trying to do here is that for every value, we'll find out first that whether the total sum I have to subtract it from the current node value. So current, the whatever siblings I have for this current, let's say, current node I am on. So if the left of it, as you can see, exist, if the left of it exists, then what we'll do is that I will subtract out the left value, okay, from the so what I've done here is that the left value is the left sum, the level sum minus other. So this other actually is calculated by finding out the node value, like if the child exists, and the, like, if the siblings exist of a parent. If the siblings exist of a parent, subtract them, and for a particular level, subtract that sibling value from the total sum of the level, and just like printing out, actually storing out that value in that particular let's say node that I'm looking for. You can just take a look at this recursion. It's not very much difficult. What I've told you is the actual logic here. And after that, we have just find out the value for a particular node. And I will again now DFS, or actually recursively call this function again for all the other nodes as well. That is going on the left hand side, the right hand side, increasing the level itself. This level is very helpful so that I can understand at which level I am on, so that I will get what is the total sum of that particular level, so that I can subtract it from here. That's it. That's the overall idea. And I have added level plus one because I've told you that I am at the parent. I'm at the parent node, and then from that parent node, I will check that whether the left child or the right side of it exists. Depending upon that, I will subtract out the value, and it's the next level. So that's why it's the next level plus. Okay, that's the overall idea and the logic for this particular program as well. You can take a look at this here as well. I will pause it from here. Okay, and you can pause it and like read the code from here as well. If you still have any doubts, you can mention it in the comment box for this particular video. I will see you in the next video, coding, and bye.